Okay, ladies and gents, can we make a start, please? Thanks very much. So, couple sort of administrative announcements before we get started. We have a special guest today, Professor Ledoux. Everybody remembers Professor Ledoux, or most do, from 2210. So, I was talking with Professor Ledoux, and we were concerned about how some of the 2210 knowledge was being transmitted to 3300, and how, like, your backgrounds and stuff like that. So actually what we've decided is that Professor Ledoux and I are both going to lecture at the same time going forward for the rest of the term. No, just kidding. Professor Ledoux is here because you might see the little GoPro down here. We're going to be videoing the lectures, and this is kind of an experiment. I'm certainly technologically challenged. Professor Ledoux is more adept than I am. But the plan is to get these posted up probably onto YouTube or something like that. So, hey, you never have to come to BMed 3300 lectures anymore if this works. So that's thing one. Thing two is that we have a quiz on Monday, so in 5 days that would be. And just to remind you, this is a 15-minute quiz. It's a closed book exam. You can use your calculators. It's going to be on material that's drawn directly from the problem sheets. So where are we with the problem sheets? I sincerely hope that you all have finished looking at problem sheet 1. Problem sheet 1 is all about conservation of mass and control volumes, right? Steady, unsteady, etc. Solutions for problem sheet 1 are posted. And that material is covered on the quiz. Problem sheet 2 is kind of this week's activity, and that's really all about conservation of balance of momentum and control volumes. I will post the solutions for problem sheet 2 on Friday after the flip session. So please, if you haven't already done so, for the people who had their recitations this morning, you've already gone, I hope, but for those of you who have afternoon recitations for BMed 3300, please go this week. Your TAs are going to be covering off a problem off of this week's problem sheet, and also we're going to do that in flip session on Friday, okay? Any questions about what's covered on the quiz? There's two questions on the quiz, real short, and it's probably a pretty good bet that one of them is going to be related to conservation of mass, one's going to be related to conservation of or balance of momentum, and they're going to be right off the problem sheets. And we're not going to ask you to go through the whole solution, probably just do a gym or something like that. Okay, remember who your friend is? Jim, yeah. Okay. Questions? Are we good? Yes, ma'am. What problem are we doing on Friday? That's a really good question. I can't remember off the top of my head, and I'm embarrassed to stand here and tell you because I did ask the TAs to prep for it. I think it's the problem with the cylinder, but I'm not 100% sure. So there's flow over a cylinder, and you have the velocity defect. Yeah, I think it's that one. Why does that matter?
Oh, I just wanted to don't do that problem.
Oh, I see. Okay, that's healthy. That's wise. Yes, ma'am.
So when an appropriate endpoint for the quiz would be like setting up an interval or something like that, and that would be like as far as we'd have to go on.
Yeah, no, there's not going to be enough time for you to solve the whole problem out unless you're like totally amazing, right? I mean, I know everybody here's totally amazing, but I mean, you can't do the whole problem, right? So it's going to be more about the problem setup, like how would you do this, and maybe how is it different from the problem. It's going to be a variation on problems that were on the problem sets, right? So how is it different from what you saw before, for example, could be a fair question. Other questions? Okay, so I know it seems like a long time ago, but last week you covered off balance of momentum with control volumes, right? So you've kind of got a couple big ideas underneath your belts now, both of them related to control volumes. One big idea is conservation of mass, right? And the second idea is momentum balance. Momentum is harder than mass, right? Why is that? Well, momentum is a vector, for one thing, so you got to pay attention to the XYZ thing. And the second thing that's harder is that you can create momentum, right? You can't create mass, but you can create momentum. How do you create momentum? You use a force to create momentum, right? F equals ma. So that leads to more complexity, and you're going to see that as you work through the problems on problem sheet 2, that they're harder than the problem sheet 1 problems, quite frankly. I think, for me, conceptually, the momentum balance is the hardest thing to wrap my head around for the BMed 3300 material. I know some students find the math more hard, but conceptually, the whole idea of momentum being transported is really weird, actually. You can kind of intuitively see that mass is transported, but, what does it mean for momentum to get transported? Well, particles have momentum, and as they move, they transport that momentum with them, right? Okay, so those are the sort of the two big ideas, and wrapped into that, of course, is the idea of defining what the control volume is, et cetera, which I hope you're getting a little bit used to. What we're going to do now, we're moving on to section or unit 3 in the course, and control volume analysis is great. It tells you useful stuff, but the big problem with control volume analysis is that it doesn't give you detailed local information. So it's great if you want to just know like a flow rate, right? Or something that's averaged. But if I want to know, okay, what is the pressure at this point here? It's really hard to get that from control volume analysis. And so what we're going to talk about today, or start talking about today, are tools that let you address the question of what is happening at this point. And I'm telling you right now that one of the challenges that you're going to experience in BMed 3300 is deciding, is he asking me, or is she asking me a question about what's happening overall? Because if that's what's being asked, then control volumes are good. Or is he or she asking me about what's happening locally, right? And just like the whole steady, unsteady thing, you kind of got to decide that pretty early on in the problem-solving process. If you don't do that, then you're going to go down the wrong path and it's going to be unhappy. So I'm going to start talking today about the tools that we're going to use to answer questions about what's happening locally at this point, right? And we're going to have some kind of fun here because we're going to end up looking at these equations called the Navier-Stokes equations, which are kind of complicated and there's some scary math in there. But the good news is that we're going to get rid of a lot of the scary parts and, bring it back down to something that's manageable. But before we do that, we're going to do something that's even simpler, which is, hey, how about we just look at fluids that aren't even moving? Right? That's got to be easier than fluids that are moving, right? And so that's what we call fluid statics, as the name implies, right? And so let's just think about, now remember we talked before about what is a fluid, and I want you all to reach back into your memory banks and ask, or think about, what did we talk about? What is a fluid? And that's going to help us answer some questions about what happens in fluids at rest. So does anybody remember what a fluid is? You all remember what we talked about? Yes, ma'am. Yes, it's an object which deforms continuously under the action of a... No. A shear stress, right? Yeah, so shear stress is really important there. Remember that there's different kinds of forces and stresses. I can have a normal force or I can have a shear stress, right? And the special thing about a fluid is, you put some shear stress on it and it deforms, and as long as you got that shear stress there, that fluid is deforming. Now, let's turn that idea around on its head. What could you tell me about the shear stresses if the fluid is not deforming? There's zero, exactly, right? Because if I have a shear stress on it, it's going to be deforming, right? So if it's not deforming, the shear stress has got to be zero. So that's a really good thing about the situation when you have a fluid at rest, because for sure a fluid at rest is not deforming, right? It's just like sitting in a jar or something like that. And so I can say right away that there's no shear stresses in there. And that makes my life a heck of a lot easier, actually. I don't know if you all remember, but we introduced that idea of the stress tensor. Remember, has that 3x3 matrix thing, and the diagonal terms are the normal stresses, and the off-diagonal terms are the shear stresses. So if you all remember that. So we had the shear stress had 3 diagonal terms, and then it had these off-diagonal terms. And the good news is that in a fluid at rest, Hey, all those off-diagonal terms are 0. Awesome. We just made the problem a lot simpler. And we're not going to prove it, but if you want to do your independent reading along the blue bar here on the side, you can also show that those 3 diagonal terms are all the same. So that complicated thing that has 9 entries in it, all of a sudden we just compacted it down to one variable. And that variable has a special name. It's called the pressure. Right? So pressure, remember, pressure is a normal stress. That means it always acts normal to the surface. Right? And that has some important implications. Let's just talk about that for a second. So, for example, if I had a container like this, and it was full of water, and I put some crazy shaped thing in that container, all right, like this little sort of potato thing that's floating in there. And I ask you, and everything's at rest in there, I ask you, what are the forces that are acting on that little potato? Right? Well, one thing you know for sure is that there's only pressures in there, right? And that means, and because pressure is a normal stress, so it always acts normal to the surface, that means that you might not know how big the forces are, but at every point on the surface of that potato, you know that the pressure is normal to the surface. Okay? So for example, here up at the top, the pressure is pushing like that. Right? Here, it's pushing normal. Here, it's pushing normal, etc., etc. So that's a pretty good thing to know, because if you're going to work with forces, you got to know directions, right? So I want you all to remember that when you have to calculate pressures in fluids at rest. Remember that they always act normal to whichever surface you're interested in. Okay? Questions about that? Okay, so that's great. We know the direction of the pressure. Unfortunately, we don't know how big the pressure is, right? And so that's kind of the second part of the discussion, which is, what is the magnitude of the pressure? Oh, little technical point here. Pressures are positive when they push against a surface, right? Stresses are positive when they pull away from a surface. It just has to do with the definition of, positive directions and stuff like that. So just remember that. If you have a positive pressure, it's pushing on the surface. I think you all know that intuitively already, right? Okay, so now we're going to figure out how big the pressures are once we know something about their direction. And to do that, we're going to do a little analysis here, a little bit of math. And what I want you to do is think about a little chunk of fluid here. So I got this little piece of fluid, and we're going to, it's surrounded by more fluid, but we're just going to focus in on that one little piece there, okay? Is that legal? Am I allowed to just kind of pay attention to one little piece of the fluid inside a bigger volume? Sure. As long as I don't break any math laws or anything like that, I'm okay. And I'm going to say that little piece of fluid is delta y high and delta x wide, and I'm going to let it be 1 unit deep into the page. All right? So we got an x, y, and z into the page coordinate system going. And the reason that I'm going to let it be 1 unit deep into the page is it's just going to make the math easier, and so I don't have to get a headache from that, okay? And I'm going to ask the question, what are the forces that are acting on that little chunk of fluid there? Well, on the left-hand side, I got P, some pressure P pushing on that side of the fluid. And remember, I know the direction there, right? Because pressure's a normal stress. So that face is oriented vertically, and so the pressure is pushing horizontally, right? On the right-hand side, I got P, but I'm going to let the pressure change with position. So on the left-hand side, I got the pressure at location X, but the right-hand side, it's not at X, it's at X plus delta X. So there could be a small difference in pressure there, and I kind of have to take that into account. Right? Similarly, on the top and the bottom, I got P at Y plus delta Y on the top and P at Y on the bottom. Right? And then I've also, you see I drew a gravity vector on there. So I'm going to worry about the weight of that fluid because that turns out to be pretty important, right? Any other forces acting on that little cube of fluid? We're not going to worry about anything in the z direction. That doesn't matter for our analysis. Did I forget any forces or stresses? Remember, there's no shear stresses. Everything's at rest, right? Just sitting there. Anything else? Am I missing anything? Did I miss anything? It seems okay, right? Yeah, we're going to go with this. All right. So now I say here that the sum of the forces has to be equal to 0. Hey, how did I know that? How do I know the sum of the forces has to be equal to 0, ma'am?
We're static.
Exactly. We're sitting there at rest, so there's no velocity, there's no acceleration. You got no acceleration, then your forces have to add up to 0. Exactly so. Okay, let's do it. So what are the forces? Well, remember, pressure is a force per area, so what I need to do to turn pressures into forces is multiply by the areas of the relevant faces, right? And so let's ask the question, what's the area of this left-hand face here? Well, this face on the left-hand side is delta y high, and it's 1 unit deep into the page. Right? This is the one time that you can get away without using units, right? So it's going to be, the area of that face is delta y times 1, or just delta y. Similarly, on the right-hand side, I got delta y times 1. On the bottom, I have delta x times 1. On the top, I have delta x times 1. And when I'm going to get the weight of that little piece of fluid, the effects of gravity, it's going to be what? It's going to be the mass times g. And the mass is going to be rho times the volume. And what's the volume of that chunk going to be? It's going to be delta x wide by delta y high by 1 deep. Right? So the volume will be delta x times delta y. So what do we got here? Let's work it through.
Sorry, what is the rho?
Density. So what we got? Here's the first part of the equation. So that's the pressure on the left times the area. That's your delta y there. Then I have to subtract off the pressure on the right. Why am I subtracting it? Well, it's pushing in the opposite direction, right? So anything that's positive x gets a plus sign. Anything that's negative x gets a minus sign. So that's my pressure difference across the little cube there times the area. And then I'm going to actually make this a vector equation because it turns out that that's useful down the road. And so what I do is I multiply that by the unit vector in the x direction. That's what that little e hat x says. So that turns that scalar thing into a vector that points in x. Right? Is that legal? Am I allowed to take a scalar and multiply it by a unit vector to get a vector? Yeah, that's legal, right? The math police aren't going to rush out and arrest us for doing that. Okay, so that's the first term. Then I'm going to do a similar thing, but in the y direction. So that's this guy here. And then the last step is, this is the weight here. So I got rho times g times the volume, right? Because I'm remembering that it's 1 deep into the page. And notice I wrote g as a vector there, so that actually accounts for the fact that it's pointing downwards. Okay. Alrighty, now what I'm going to do is I'm going to divide through by delta x, delta y, and when I do that, I get this equation here. And I want you all to look at this term. So what is that first term there? Or maybe it's easier to see if I flip it around. So what is p at x plus delta x minus p at x divided by delta x? I'm going to let delta x get really tiny, so what would that term become? It's the derivative of p with respect to x, right? Because what does that mean? Derivative of p with respect to x is I take the small change in p and I divide it by the small change in x, right? So this term here gives me actually negative dp dx because I got to flip the sign. This term here gives me negative dp dy, and when I make those substitutions, I end up with that equation there, dp dx times e hat x plus dp dy, etc., etc. And then I hope you all have looked at the Tegrity lecture on math fundamentals, and you say to yourself, oh yeah, that looks familiar. Because if I have dp dx times e hat x plus dp dy times e hat y, that's just the gradient of p. Right? And so my equation just comes down to grad P minus rho G equals 0. Congratulations, you just derived the equation that governs how pressure changes in a fluid at rest. Now you know everything about the pressure because you know the direction, because we know it's normal, and that equation tells you how it changes with position, as we'll see in a second. Sir, ma'am?
Why was rho gravity positive first and negative going down?
Oh, because I had to flip the... I'm not sure I understand your question. Ask it again, please.
Well, because Ty for us was positive, and then it was minus Ty and G was the same direction.
Yeah, but remember that this is in the y direction, right? But this is in the g direction. That's the gravity vector. All right, so g is pointing downwards. Yeah. Other questions? Yes?
How come you ignored the z component?
Oh, because it's too complicated. We would get an exact similar term that's dp dz times e hat z, but it's just too painful to write out, you know. Yeah. Yes, ma'am.
Didn't you say that the pressure is positive when pushing on such?
Correct.
So why are all of the pressures around the reactor not positive? Because they're all pushing in on.
Oh, they are all positive, but when we do our force balance here, right, when we do this guy, we have to take into account directions, right? And so x is when we do our x direction, x is positive rightwards. So any pressure that's in the left to right direction gets a plus sign, but any pressure that's in the right to left direction gets a minus sign because it's pushing against x. So it's a positive number, but it's pushing in the negative x direction. Yeah? Other questions? Okay, so if we do all that, we can actually that equation there tells us a couple of things. Oops, excuse me. That equation tells us a couple of things. The first thing it tells us is that if I move in planes which are normal to the g vector, so in other words in horizontal planes, then the gradient of p is 0. Or in sort of plane speak, that means that p doesn't change. So that's called Pascal's Principle. If I move on a horizontal plane, the pressure is the same. So in other words, here the pressure is some value, and here the pressure is the same value, assuming that the air in this lecture theater is still, which it isn't quite, but that's a pretty darn good approximation. Okay? Be careful, that only applies inside continuous bodies of fluid. So like if I had some kind of a separation between, like let's say I had like an aquarium here or something like that, and I had the air outside and the water inside, they were both at the same level. It's not the same body of fluid, so I can't go on horizontal lines if I jump between bodies of fluid. But as long as I'm in the same body of fluid, pressure on a horizontal plane is the same everywhere if the fluid's at rest. Okay, that's the first thing. Second thing is that in the direction of the g vector, I can simplify that vector equation down to the simpler dp dy is minus rho g. And that basically tells me how pressure P changes with Y. Hey, isn't that what I wanted to know? I wanted to know how pressure changed with position. That equation is telling me pressure only changes with Y. So in other words, if I go up or down, the pressure changes. If you've ever gone scuba diving, you know that, right? It's all about how deep you are. You know, that's what controls the local pressure. Now, G is a constant. In some cases, rho is not a constant. Like in the atmosphere, if you were going to calculate the pressure distribution in the atmosphere and you were going to go like way high, as you go higher, the rho changes. And so that equation gets complicated. But For BMEs, we don't care so much about stuff like that. We'll leave that to the aero guys. And so for purposes of what we're going to talk about, we're going to treat rho as constant. And if we do that, then we can integrate that equation really easily. We just take dy up onto the right-hand side and integrate both sides. And we get this really simple formula here, which is P is P naught plus rho GH. So what does that mean? It means that the pressure inside this body of fluid here is equal to the pressure at the surface, so I call that P naught. And by the way, whenever I draw a little triangle like this, it's like a little thing floating on the surface, so that's supposed to represent an interface between like air and some liquid. So the pressure inside the liquid here is equal to the pressure at the interface plus the density of the liquid rho, the gravitational acceleration, that's a scalar now, right? It's not a bold anymore. And the depth, h. It's basically telling you the deeper you go, the higher the pressure gets, right? That's a pretty simple formula. The one mistake that you can make, and it's easy to do this, is that you can get the signs the wrong way around, and you can make the pressure get bigger as you go up. So don't do that. Just like in the back of your head, every time you use that formula, say, did I get it the right way around? Like, is the pressure getting bigger as I go deeper, right? And if you did, then you're good. Yes, ma'am.
How did the sign change from minus rho to y?
Yeah, because in our, the way we defined it, y points up, but h is downwards. Yeah. Sorry about all the sign changes. This is kind of following along the way they do it in the book, so it's a little, yeah, maybe one too many sign changes in there. But if you get one thing out of this section, I want you to remember this formula here, okay? Now, I hope you also all see that there's an intimate relationship between pressure, P, and the height of fluid, right? Like they're exactly proportional to each other. So that, I hope that makes it clear to you all what the idea. So have you heard of pressures expressed in millimeters of mercury? Right? Like you get your blood pressure, 120 over 80. What does that mean? 120 over 80. What's your, what is systolic and diastolic? So what does systolic mean?
Before the heartbeat.
No, it's
at the ventricle contracting.
Yeah, so basically it's your peak pressure. So systole is the contraction phase of the left ventricle, right? So that's your peak pressure, and then diastole is basically the rest of the cardiac cycle. So that's your lowest pressure. So that's why they always, give it as two numbers, 120 over 80. You got your systolic and your diastolic, but they never tell you that the units for that are millimeters of mercury, right? And now you know that the 1 millimeter of mercury of pressure is equal to the pressure that you get from a little tiny column of mercury that's 1 millimeter high. Right? Do you know why they use that as a unit of pressure? Like, why did the unit millimeter, it doesn't, like, not an obvious thing, right? Why the unit of millimeter of mercury? Why did they use that? Anybody know? Yeah, in manometers, but what's special about mercury? It's the only metal that's liquid, at least at room temperature, yeah. But why is that special?
It's a lot denser than water.
It's dense. It's dense as anything, right? So I can get, yeah, exactly. I can get 1 atmosphere of pressure is 760 millimeters of mercury, so that's about that high, right? So I can do with a pretty short tube in mercury what it would take me like a really, really long tube in water to do. Right? So it's just convenient to use in the lab. There is this small problem that mercury is unbelievably toxic, right? But, they sort of didn't figure that out or know that when they were first starting out. So you might be amused as BMEs to know that at the very beginning when they were, like, because, they didn't actually know what blood pressure was until I think like the 1700s, something like that. And they don't do this at home, okay? But they literally, cannulated a vessel, hooked it up to a manometer with mercury, so the blood was right in contact with the mercury, and measured the pressure in the, on the height of the mercury column, which, if something goes wrong, that's not a good situation, right? But so do you all understand what the pressure of 1 millimeter of mercury means, right? And there's also sometimes you see pressures in centimeters of water. So that's how much pressure you get from 1 centimeter of water. And sometimes you'll see pressures expressed in inches of water, feet of water, whatever. It's equivalent height of a column. And you can convert between the height and the pressure using this formula here. Okay? Questions about that? All righty. Let's do a little example here. So I got a bioreactor tank, and it's full of some stuff, maybe some bacteria that's making some recombinant protein for me. And I want to know what the pressure in that tank is, because if it gets too high, the tank's going to blow up, and that's going to be bad. And unfortunately, my digital pressure meter wasn't working that day, and so I had to go old school and use a manometer. And though this is what we've got here, a manometer is just a tube with kind of a U-bend in it, and it's filled up with some fluid with density rho sub 2, and the pressure in the tank pushes down on that interface by the B there and pushes the manometer fluid up the right leg of the manometer. And from knowing something about those heights, D1 and D2, I ought to be able to figure out what the pressure in the tank is going to be, right? So that's what I'm asked for in this problem, is to derive an expression for the pressure in the tank at level A in terms of the density of the fluid in the tank, rho 1, the density of the manometer fluid, rho 2, D1 and D2, and anything else I might need, okay? Everybody understand are we good on the setup of the question? Ma'am, does that make sense to you? Yeah. So how are we going to do this? Well, we're in the hydrostatics section, and we're going to assume that everything's at rest here, right? So we know that P is P naught plus rho GH, but this is a little complicated because we kind of got two different fluids here, right? And we sort of got to put it all together somehow, and it's not totally obvious when you first look at it how you should do that. So the trick to these kinds, or trick, I don't know if it's a trick, but the way that you solve these kinds of problems is as follows. Start where you know something, and then work your way along the chain. So what does that mean? I actually know what the pressure is here, right? Because that's open to the atmosphere. So I know that it's atmospheric pressure, whatever the barometer reads that day. And then I know that P is P naught plus rho GH. I can get the pressure here, right? At this level. Because I can use my hydrostatic formula down that column. So I know the pressure at C. Now, what's the pressure at B? It's the same as at C, right? Because it's at the same level and it's all inside the manometer fluid. So I can just kind of jump across the legs there. And then the last thing I can do is go, so I'm good, I'm at B, and then I just have to go to A, right? Now be careful. When I go from B to A, I'm going up, right? So what does that mean the pressure's doing? It's getting less, right? You see, it would be easy to make a sign mistake there, and then you'd get into trouble, okay? So just be really careful about sort of your accounting on what's above and what's below and these things. And the other thing I need to do here is that when I'm working inside the manometer fluid, I have to remember to use the density rho 2. But when I'm working inside the fluid in the tank of the bioreactor, I have to use rho 1. So you just kind of have to be a little bit organized when you do it, right? If you follow the rules, then you're going to be good. So what do we got here? I'm going to refer to the pressure. Okay, so it's got something weird going on with my pen here. Yeah, I'm not sure. I'm sorry about this. My pen is misbehaving. This is a new computer here, and it's like, oh, it hasn't done this before. So here's my equations here. I'm going to say that P naught is the pressure up at the top there. Right? That's the atmospheric pressure. So the pressure at C minus P naught is rho 2 G D2. Right? That's the... And, okay, is P at C bigger than P naught? Yeah, it is, because I'm going down, and this is a positive sign, so I'm good here, right? I use the fact that P at C equals P at B, and then this is my pressure difference inside the bioreactor fluid. And here, I'm careful. Again, P at B is bigger than P at A, right? So that's a positive number, and so that's positive, so I'm good, right? So what have I got here? I got 3 equations for 3 unknowns. My 3 unknowns are P at A, P at B, and P at C. So I got to do like a little algebra there to get rid of all of those messy unknowns. And when I do that, I end up with a pretty nice simple expression for the pressure at A, which is just given by this equation here. Right? It says the pressure at A minus P naught is rho 2 D2 minus rho 1 D1 all times G. And I would ask you to just go through that little math exercise at home to make sure that you get that same answer, okay? And that is correct. There's something I'd like to point out to you about that. You notice that my answer has atmospheric pressure in it. It has P naught in it. And I can never get rid of that, right? That's because when I do that analysis, I have to start at the free surface, which is like up at the atmosphere, right? It's at P naught. And try as I might, it's always going to come in. And because that happens so commonly, we actually have 2 kinds of pressures. And I just kind of ask you to remember this. When you measure a pressure with respect to the atmosphere, which is what we're doing there, right? We're getting an expression for P at A compared to P naught or minus P naught. So that's measured or expressed with respect to atmospheric pressure. We call that a gauge pressure, because that's usually what you read on a pressure gauge. Right? So if I say to you, you know, like when you do your blood pressure, your systolic, diastolic blood pressure, that's a gauge pressure. Right? It means that the pressure in your vein, or your arteries, is that much higher than atmospheric pressure. There is another kind of pressure that's called absolute pressure, and it's kind of like, you know, Kelvin versus C. You have to add on some kind of an offset. In our case, for pressure, the offset is the atmospheric pressure at that location at that time, right? So what's the atmospheric pressure? Anybody know what a good number for atmospheric pressure is? 1 atmosphere, yeah. Yes, that is a unit. That is the atmospheric pressure. That is correct. 760 millimeters of mercury, exactly. So actually, when they measure a pressure of 120 millimeters of mercury at systole in your brachial artery here, it's an absolute pressure of 880 millimeters of mercury. 760 plus 120, right? What's atmospheric pressure in SI units?
10,000 pascals.
Out by a factor of 10. 101,325 pascals, or 101.325 kPa. Yeah. You don't know that off your head? Top of your head? Alex, come on. Okay, any questions about this? Are we all good? Okay. This hydrostatic stuff is not that complicated, right? Just, get your signs right and then you're good. Okay. All right, let's talk quickly about buoyancy. You all know what buoyancy is, right? When you put something in the water, if it's light enough, it floats. And that's telling you that there's a force that's pushing it up inside the water, right? And there's different ways to think about that. One way to think about it, which is kind of a conceptually nice way to do it, is that let's say I have some object and it's floating underneath the surface of the water. And you could say there's a force pushing down on that object from the top. And there's a force pushing up on the object from the bottom due to what? Due to the pressure, right? So the pressure is pushing on the top, the pressure is pushing on the bottom. And I'm a little cavalier with directions here because you know that pressure is normal, but actually when you integrate over the surface, you have to have a net, like vertical force there. And I would contend to you that the pressure is bigger on the bottom. Why is that? Well, we just talked about it. When you go down in a body of fluid, the pressure gets bigger, right? So force bottom is bigger than force top, and so there's a net upwards force, and we call that the buoyant force. All right. And who is the guy who figured out the formula for buoyancy? The Greek guy back in the old days? Archimedes, exactly. And what was happening? Anybody know the story? He was in the bathtub, yeah. But hang on for a second. Why was he thinking about buoyancy?
The king wanted to make sure that the crown was actually made of gold.
Exactly. Oh, we have a scholar here. Yeah, very good. Yeah, there was a question. The king, I think he had a crown made for him, but he didn't know if they kind of like cheaped out on it and just put gold on the surface or if it was really gold all the way through. And he asked Archimedes to figure out if it really was gold without like sawing it in half. And Archimedes got thinking about, buoyancy forces and could you figure out something, based on the density, et cetera, et cetera. But he didn't know what the formula for buoyancy was, and he was taking a bath. And then it came to him, and he was so excited he like jumped out of his bath and he ran down the street naked, shouting, Eureka! Yeah, exactly. So Archimedes' formula, it's really a simple formula. It says that the buoyant force, F sub B, up at the top left there, is rho times G times what we call the displaced volume. Now, there's two tricky things about that formula, and you got to be careful. There's only 4 terms in it, so 2 tricky things is bad, right? The first tricky thing is the rho that you use is the rho for the fluid. Do not use the rho for the object that's floating. That's thing 1. Thing 2 is that V disp is what we call the displaced volume. And that's basically, you can think of it as, it's the volume of fluid that is kind of made to get out of the way by the object or is displaced by the object. So when the object is underneath like this, completely underneath, then the displaced volume is the same as the volume of the object. But if I have something that's floating and some of it's above the water and some of it's below the water, I only count the part that's below the water. That's my displaced volume. Okay? And the last thing you need to know is that the force is always upwards, at least on Earth. Okay? And I know you're all thinking, oh, that's easy. Wait till you do question 5 or question 6 on the problem sheet this week. And you're going to find out that actually the whole displaced volume idea sometimes isn't as straightforward as you might think it is. Right? You got to think about that one a little bit. Questions about that? Sir, you good?
I'm good.
Yeah. Ma'am? Okay. All righty. I now want to talk to you about something called fluid rheology. So we're going to shift gears here, all right? Everything we talked about up until now in this lecture has been about fluids at rest, right? Hydrostatics and buoyancy. Now we're going to start talking about fluids moving. And it turns out that when fluids move, it's a little more complicated when they're at rest. And the first thing we need to do is introduce this concept of rheology. So rheology comes from rheos, it's a Greek word, and it basically, it's the study of the relationship between force and deformation. And you all have done this before, right? Like if I said to you, I have a linearly elastic isotropic solid, so perfect solid. You could relate force and deformation for that solid to me, right? What's the formula?
PL over EA.
Say again, please.
PL over EA.
PL over EA.
For deformation.
Yeah, so deformation is PL over EA. Or in a more fun, like if I wanted to say that in terms of stress and strain, what would I say? Yeah, it's a serious handicap that I can't actually write on my screen here. Okay. Does that look familiar to anyone? Stress is equal to big E, Young's modulus, times epsilon, right? What's Young's modulus named after? Thomas Young. He was a famous guy. By the way, he did a lot of bioengineering, but back in the 1600s when they didn't teach it at Georgia Tech and stuff like that. If I want to know if I want to know Young's modulus for a solid, for an elastic solid, what do I do? Yeah, I could divide the stress by the strain, but that would require me to do an experiment. Too much work, right? Yeah. Wikipedia, Young's modulus, what's the value, right? It's a material constant. There's stuff, I don't know if they have Young's modulus in the back of the textbook, but you can look it up on the internet. It's a property of the material, right? That's great for solids. It totally does not work for fluids. Why does it totally not work for fluids? What's epsilon for a fluid? Sorry? Unknown, but why is epsilon? Yeah, it's true. Why is epsilon unknown for a fluid? Because it continuously deforms. So what does that mean that epsilon is? No, it's not zero. Yeah, if you wait long enough, epsilon is infinity, actually, right? It just gets bigger and bigger and bigger for as long as you're applying a stress. So that's a problem. We can't use that formulation for a fluid, right? That's problem one. There's another problem. When I think about the simple Young's modulus experiment, so I have a little block of aluminum or something like that, and I pull on it and stretch it out and see how much longer it gets. What kind of a stress am I applying to the block when I do that? Is that a normal stress or a shear stress? Really? Yeah, I think it's normal, right? Ma'am, can I borrow your pencil case here? Thank you. This is very nice. Where did you get this? Really? They have the coolest stuff in Japan. I love going to Japan. Next time you go, could you get me one? Yeah. Okay, I'm sorry. This is my block of aluminum, okay? And I'm going to pull on it. So here's my force in this direction on one end, and I got the same force on the other end, right? So what kind of a stress is that? So here's my face, right? The normal is in this direction, and the force is in that direction. So that's a normal stress, right? But in fluids, thank you. In fluids, what's the kind of stress that we care about more? It's a shear stress, right? Because that's kind of all bound up with the whole definition of a fluid. So that thing doesn't work for fluids in two ways. Uses normal instead of shear and uses epsilon instead of something else. So what we want to do is come up with something that's like that but it's for a fluid and it works, all right? And we'll talk more about it next time, but I'll just tell you quickly that sigma gets replaced by a shear stress, and epsilon gets replaced by the rate of change of epsilon. So it's not how much the fluid deforms, but it's how quickly it deforms, right? So I'll see you all in flip session on Friday, okay?